Hi, my name is Kefeng Jiang. I'm a first-year graduate student working in Dr. Bali's quantum optics lab at Miami University, Oxford. In this experiment, we investigate practical realization of long-distance quantum communication and quantum memory using electromagnetically induced transparency, or EIT media. Photon, particle of light, is a fundamental carrier of information. It can carry information in its frequency, phase, polarization, and so on. It is fast and robust. Light pulses typically travel with a group velocity close to 3 times 10 to the 8 meters per second, the speed of light in vacuum. Controlling the speed of light pulses or storing light pulses is then critical in long-distance quantum communication and quantum memory. These typically can be achieved by the ability to couple light to a resonance system like an ensemble of atoms. In our case, warm alkali vapor cell. The vapor cell is inside this 3-layer mu metal shell, which is used to block the Earth's magnetic field. With a solenoid and heating wire, we can precisely control the magnetic field and the temperature of the vapor cell. A phenomenon called electromagnetically induced transparency can be used as a technique to provide a controllable atom-like coupling which allows the manipulation of the optical property of the atomic medium. So what is EIT? EIT is a two-photon or two-optical field effect where a control field can greatly reduce the resonant absorption of a medium to a second signal field. When the signal field propagates through the EIT media, it will experience a steep resonant dispersion. This steep resonant dispersion will reduce the group velocity of light pulses significantly. In our lab, we can slow the light pulse down to around 300 meters per second, which is a millionth of speed of light in vacuum. The slowest light pulses have been made through EIT has a group velocity of 8 meters per second. The fastest human being boat can run 10.4 meters per second, which is faster than that. Furthermore, reduce the control field to zero effectively reduce the group velocity of signal pulse to zero and stop the pulse. All the information carried by the signal pulse will be mapped into the collective atomic ground state coherence. Turn the control field back on will invert that process, thus retrieve the signal pulse. Our team have achieved a storage time of around 500 microseconds. Our next step is to store information imprinted in the transverse plane of the probe or an image. When the image stays in the EIT media, diffusion of the warm alkali atoms will distort the image. Fortunately, there is a type of beam called Laguerre-Gaussian LG beam, which has a donut-like transverse profile. The dark center of the donut profile were proven to be robust to diffusion of atoms. Recently, we have already generated the LG beam by spatial light modulator, and we are working on its storage. Image storage can provide a higher numeral-based system than the binary numeral system. Consequently, you will increase the data rates due to reduce the number of bits needed. Thanks for watching.